Hello, and again, we're going to keep talking about some review of special right triangles. And as I prompted in the last video, we're also going to talk about radians as another unit for angles that is a possibility on your calculator and also by hand. So, if you remember our special right triangles, there's two of them. They are named for the angles that they have in degrees. So we have our 45, 45, 90 triangle, and we have 30, 60, 90 as well. And these have a constant ratio between the sides, and these are the, basically these end up being the values for sine and cosine and tangent that you can figure out exact values for instead of using decimals to estimate, since the vast majority of trig ratios are irrational numbers. So for the 45, 45, 90 triangle, because we have two congruent angles, we also have two congruent sides. So whichever one this is, then the hypotenuse is that number times root 2. This is the one students generally remember best. Now, in our special right triangles, the shortest side can be whatever x. The hypotenuse is going to be twice that length. So what I always tell students is that, look, there's a 2 on the hypotenuse, but here it's in a root, and here it's not. But you always have a 2 on the hypotenuse, which just makes it easier to remember. And then x is always on the shortest side. So we've got an x here and x here. The long other side of the 30, 60, 90 triangle is x times the square root of 3. And what this just is helpful to remember is 2's on the hypotenuse, and then the root is on the largest number. So here we've got 1x, 2, 3, and then the root goes on the 3. Here we've got 1, 1, 2. The root is on the 2. If you haven't memorized these already, that's a nice kind of rule of thumb. Now here, as I said, it's a nice way to evaluate the exact values of some of these trig ratios that if you type them into your calculator, you get an irrational number. So in number 1, it says, evaluate the following trig ratios. So here we have cosine of 30 degrees. If I look at these special right triangles over here, here's my 30 degrees, which means x is my opposite, x root 3 is my adjacent, and 2x is my hypotenuse. So if I'm looking at cosine, as we remember, is adjacent over hypotenuse. And from the 30 degrees, adjacent is x root 3, and the hypotenuse is 2x. Simplify. And we can tell then that the cosine of 30 degrees is root 3 over 2. You can check this on your calculator if you want. Just type in root 3 divided by 2 and type in cosine of 30, and you'll see that you get the same irrational decimal. Now, tangent of 45, we're going to use our 45, 45, 90 triangle. You could use either of these, but I'm going to use this one. I've got my opposite, which is x, and my adjacent, which is also x. So for tangent, which is opposite over adjacent, well, the opposite is x, the adjacent is x. So the tangent of 45 is 1. So this is great, very easy to check on your calculator as well. As promised, we're also going to talk about radians. Now, radians are just another unit for angles. So just like degrees, radian is just a unit for angles. And there is a conversion rate between them, just like meters and inches are another units to measure length. And 360 degrees is equal to 2 pi radians. And the reason it's called radians is 2 pi r, which is the shorthand, radians, is a total circle. So 2 pi r circle, and 360 degrees is also a total circle. So you might also use the conversion factor of pi radians, and you can write it as a fraction for stoichiometry, which is what we'll be doing sometimes, is 180 degrees, which is just our simplified conversion from 2 pi is equal to 360, pi is equal to 180. Now, convert the following angles into radians. So I will often for this use stoichiometry, meaning that I will say, all right, I have 60 degrees here, and I want to multiply that by a conversion fraction. I'm going to have degrees in the denominator so that the degrees cancel out, and then radians in the numerator because that's what I want it to actually turn into, and that's going to be the unit I'm left with. Then I just use these conversion factors, put 60 over 1, and say then this is pi 180, simplify. So 60 over 180, cancel by 10, divide by 6, pi over 3 radians. Now, radians are helpful for a lot of things. Degrees are helpful for a lot of things. Different units are good for different types of problems. So it's nice to be able to switch back and forth between these. If you want to see another practice of this, you can look at the attached PDF. Let's look at 3A. So here it says convert the following angles into degrees. Now, one thing you'll notice is that if it doesn't say, here it always says degrees. Radians don't always say radians, but by context clues, if you see an angle measure with pi and no degree sign, that means that it's in radians. So it's just a weird unit that they don't write the unit for. Do I understand why? No, but it's a fun, zesty new world. If you see pi and you don't see a unit and it's about an angle, you have to be able to infer that you're talking about radians. You'll get used to this, I promise you that. So here we have pi over 6 radians, and we want to turn it into degrees. So I'm going to do the same thing here. The nice thing about radians is they're often fractions, so you just leave it as the fraction, radians. And then what I multiply by the conversion factor, degrees and radians, so they cancel out. And I'll use the same one, pi over 180, except for it's 180 with the degrees is in the numerator now. And pi radians is in the denominator. Pi cancels, and we end up with 180 degrees over 6, which is 30 degrees. Again, if you want to see a second example for 2 pi over 5, look at the PDF attached. In number 4, it says sine of pi over 4. Now, since radians are brand new, I often recommend to just convert to degrees to start with. You'll get used to radians and you'll stop having to convert all the time. But for the first part, I'm just going to convert to degrees. So if I have pi over 4 radians, just like I did in the problem above, I'm going to convert to degrees, cancel out radians, and I'll use 180 and pi. Pi cancels, radians cancel, and I end up with 180 divided by 4, which is 45 degrees. So what this is really asking now is what is the sine of 45 degrees? I'm going to use my special right triangles, and as we recall, if I have 45 degrees here, my opposite is x, and my hypotenuse is x times root 2. So the sine of 45 degrees is equal to the opposite over the hypotenuse. And I'm going to simplify, so x over x root 2 simplifies to 1 over root 2. Rationalize the denominator. And my final answer for sine of 45 degrees is root 2 over 2. If you have questions about any of these things, please don't hesitate to ask, and make sure that you're nominating everything that you're stuck on in the form, and I will post videos about those on Wednesday.